Good morning everybody. Today I am going to take online class on transformers with particular emphasis on one aspect of the transformer, that is the regulation aspect. But before that I would like to review the some of the topics that have been covered in previous classes, because some of the concepts are very important, and I will just try to review them and emphasize a few important things about the transformer. So, first I start with one idea that, so I am just doing transformer, and basic objective of today's class is to transformer. The basic objective of today's class is to look into the regulation aspect of the transformer. Regulation, I am doing a little advanced compared to the other sections, because my previous professor has taught a few important aspects of the transformer already. So, essentially before going to regulation, this is the regulation of a transformer. Before defining it and before going to that, I will try to teach review a few previous subjects, like which I think is very important. What is in fact what is the difference between a transformer and an inductor. These are, both of them are very important components of electrical network, and an inductor, transformer and an inductor. Both of them are magnetic components. First point is that let us look at the similarities. The similarities that the transformer is a magnetic component and inductor is also a magnetic component, and both of them are sometimes defined in terms of inductances. Inductance is an transformer is not really defined in terms of an inductance, but inductance comes while defining the performance of a transformer. Similarly, inductor is always defined in terms of an inductance. So, what is the difference? The philosophical difference between an inductor and a transformer is this: inductor in an electrical network is used for storage of magnetic energy. Okay. So, I will try to clarify what do I mean by storage. So, it is normally a one port device. So, inductor is normally a one port device. That means, it has essentially two terminals, and through those two terminals, that means, if I look at a black box, if I look at an inductor as a black box, this is an inductor as a black box, there are only two terminals, and these are the terminals, that are used to connect the inductor in an electrical network. So, what happens in an inductor is constructed in such a way, its construction is such that it can store energy. That is the job of the inductor. So, energy storage here, one interesting point is that storage may be stored energy also implies that this, since the network current, if the current is an AC, so what we will see that during some portion of the AC cycle, of the AC, inductor will actually take energy, remaining part of the AC cycle it will give back it will return back the energy to the external to the energy to the external circuit. So, its method is such that some portion of AC cycle, inductor will absorb energy from the external network, and during the remaining part of the AC cycle it will return back the energy in the, so that overall there is no energy consumption. So, overall over this cycle there is no energy consumption in an inductor. So, this is how the inductor really philosophically works. It is supposed to store energy. Now, it may so happen that it is possible, though I am saying it is basically a 2 terminal network essentially, but it is possible to have construct more terminals possible, but then also its job would be in the magnetic structure. This is magnetic structure. In the magnetic structure it is possible to have 2 terminals, but it will be similarly doing through 2 ports, this port as well as this port, energy will come in and get stored in the magnetic structure, right, magnetic structure. This is the essential functionality of an inductor, whereas the transformer's job is not to store energy. Whereas, if I look at a transformer as a black box, magnetic structure of a transformer, here this magnetic structure stores no energy even in the instantaneous basis, even in the instantaneous sense, it never stores. So, what happens is transformer is normally created with 2 terminals, 2 ports, port 1 and port 2 has to be. Most often it could be more, it could be even more, but at least 2 ports, 2 electrical ports, 2 electrical ports. So, what it means is that it stores no energy. So, when instantaneously current is going in, the energy that is going in, energy in through current I 1, energy in must be going out, energy out. The energy is then going out through port 2, and energy means it is also has to be a product of voltage. So, V 1 I 1 indicates the energy in, V 1 I 1 product indicates the instantaneous power, V 1 I 1 indicates the instantaneous power in, must be equal to V 2 I 2, must be equal to V 2 into I 2, instantaneous power output. So, what is most critical in a transformer is that this relationship V 1 I 1 is equal to V 2 I 2 is maintained, So, that is what in, though it may have even more terminals, even more terminals, but otherwise even more terminals is possible, but then you write the balance equation, energy in is equal to energy out, energy in summation of energy in and out. If I take the proper convention, then it should be equal to, if I take the proper convention of all inside, then that summation of that could be equal to 0, but let us not complicate ourselves. Most often the transformers are 2-port devices, like energy 2-port electrical devices, energy is coming through one port and energy is going through another port. Normally this so basically the magnetic structure point, from the magnetic structure point of view, what is the difference? So, how do we do that? The next question, follow up question is, how is it possible that in one magnetic structure we store energy and in another magnetic structure we do not store energy? How is it possible? So, the possibility, I am just reviewing it, probably in previous classes you have already realized this possibility exists because inductor magnetic circuit has air gap, and you may be surprised, but energy is stored in the air gap. Energy is never stored, energy is always stored in the air gap, never not in the magnetic material. The reason for that is that magnetic material has because the magnetic material has very high permeability, very high mu r. Mu r is the relative permeability, very high mu r compared to the air, compared to the air. So, inductor magnetic circuit has air gap. Energy is always stored in the air gap, not in the magnetic material, because the magnetic material has very high mu r. Therefore, its reluctance, the reluctance of the magnetic material, magnetic path through the iron, magnetic material, you already know the magnetic material could be a ferrite or it could be an iron. So, this iron and ferrite has very high permeability. So, if it has very high permeability, its reluctance is very low. So, if the reluctance is low, there is no energy that can be stored, because the energy storage formula is roughly phi square into reluctance, just like our resistance I square into R, a similar formula is phi square into R. R is the reluctance in this case. So, the reluctance being low, it cannot store any energy. So, there has to be a creation of an air gap in the inductor magnetic circuit, and in there then the energy stores there. So, obviously therefore, the difference is that in a transformer, when there is a magnetic circuit, you should see that there is no air gap, or air gap is as, obviously due to mechanical connections and contacts there will be some very small air gap, but our intention would be the transformer should not have any air gap. Transformer magnetic circuit should not have any air gap. We will see the consequence for that. So, this is the philosophical difference between a transformer and an inductor, and how that is used in an electrical network. In the electrical network, we use transformer for transfer of power. Power is in and power is coming in through this port and power is going through this port, coming in power and going out. That is what is the transformer's basic role. Then there is also another very important role. Transformer is doing a very important job of so called creating a galvanic isolation. So, that means the reference voltage, the reference here, this may be the reference node of the side 1, this is the reference node of side 1, and this may be the reference node of side 2, reference of side 2 terminal, and there is no really definable voltage between these two, they are completely floating voltage. Between reference 1 and reference 2 there is a galvanic isolation. So, reference 1 potential is not defined with respect to reference 2, it is not defined, it is completely floating, we call it floating. So, this floating potential is creating a kind of thing called galvanic isolation. So, transformers are doing a very beautiful thing, it is providing a galvanic, which is very important for safety purpose. So, galvanic isolation. So, it transfers power with galvanic isolation and simultaneously it scales voltage and current. One is consequence of the other. So, if the power is unchanged, if there is a scaling in the voltage, there must be a scaling in the current, as we see is here, V1 I1 is equal to V2 I2. Please note that again I emphasize this voltage equation is instantaneous equation. It will obviously follow, it will obviously satisfy the RMS value equation, but actually this is an instantaneous equation. This V1 I am writing with subscript small value small v to indicate that it is a function of time. I am indicating that V1 is something like Vm sin omega t, V max sin omega t, that is such kind of expression. So, it is a sinusoidal expression when V1 is an instantaneous voltage. So, instantaneous voltage into instantaneous current, at that moment the current at the same instant must be matched to instantaneous V2 voltage multiplied by the instantaneous current in from the secondary port. This is secondary port current, this is called port 2 current or secondary port current. We normally name one port as primary and another port as secondary. The convention is being that the port in which the voltage source is connected is named as primary, and the port in which the load is connected is named as secondary. So, this is to be remembered that transformers basic objective is to produce galvanic isolation and transfer power with the scaling of voltage. So, this is the basic objective of a transformer. Now, let us take one more concept that sometimes we are little bit uncomfortable, that is the convention of a dot and a cross terminal of a transformer. Dot and cross terminals identification. This is a thing we sometimes face a little bit of difficulty or in designating this kind of dot and cross terminal. So, now I am doing a simple two dimensional structure of a transformer, Let us see that two dimensional transformer is, this is the magnetic thing core, this is the core, as you have already learned that this is this has very high permeability, mu r is very high permeability we put, and we put a coil, and we put a coil here, and we put a coil, another coil here. Right. We put another coil here. Though I have drawn it as if the number of turns are equal, the number of turns can be different. So, number of turns may be called N1 and N2. I hope you do not have any difficulty in understanding the way it has been wound. It has been wound this way, going up, then coming from the below, and then coming up, and then going here, and then another one is also going up this thing. Now, just from this we should be able to identify which terminal we should think as a dot terminal. But is this the only way we can wind it? No, we can see that we can wind it another way. Let us see another way we can wind it. Primary I am not changing, primary you can see that I am maintaining the same way of winding the coil, same orientation of rotation, and then secondary side I am changing it. Secondary I am changing it this way. Right. Okay. Do you see the change? Do you see, first observe the secondary, this secondary, let us give some names, let us give some names, let us call it these terminals A1 and A1 and A2, let us call it, or A1 dash, let us say A1 dash, and this is, we let us call it B1 and B1 dash. Right. So, this is the essential structure, this is formed of magnetic material and a coil is wound, and then there is another, this is two versions of the transformer I have shown. One case the winding is done this manner, in another case this winding is done in this manner. Let us name it as C1, let us name it C1, let me call it A2 and A2 dash, and this let us call it C1 and C1 dash, right. So, how do I put dot convention in these two structure? The rule is very simple, very simple. You first, listen to me carefully, you first put a reference current direction at any terminal of this side, Let us say the reference current direction is this, reference arrow direction is this. Let us say the reference current direction is this. Now, with this current direction, and I put this terminal as arbitrarily a dot convention. Dot can be thought of as plus also. There is no nothing very specific about it. Dot or plus. If I use dot, I will use dot and cross. If I use plus minus, I will use plus or minus. So, what I am doing is, first I am referencing a current. And putting a dot at that terminal, referencing a current and putting, I could have put the current direction in the other way and also could have put the dot here. So, just referencing and dot I am putting here. Now, with respect to that, I will decide which terminal is dot and this in this case. So, I have to decide now whether this terminal, I have to decide here, I have to decide which terminal is dot. Which one is dot here, dot terminal here, I have to decide that. So, what I do is, first I look at it this way, if this is the current direction, then I, from the right hand law, right hand rule, I know the current flux direction is going like this, flux lines would be going due to the current in this, it will be going like this, right. Then in my mind, it does not require anything, in my mind I just think that I have to decide whether B1 terminal is dot or not, I have to decide B1 terminal whether it is dot or not. What I do is, I put, since it is in my mind, I simply think that there is also another current that is in through this terminal, If due to this current, let us call this current as I2 and this current was I1. If due to this current, the flux that is produced, the first one was flux created by the current I1. This was, I can say that the flux lines are created by the current I1 due to I1. I can think that these flux lines are created due to current and this arrow of the flux line is this. Now, due to the current I2, what is the flux line created? This is, let us say, due to current I2, we know that again right hand thing, flux lines would be created in the similar way. Similar arrow direction. If this happens, that means arrow direction in, this terminal arrow direction current is in and the flux lines is in the similar direction, then I define this terminal as same as this terminal. I could have started the name as this as cross, there was no problem, I could have defined as cross. If I had defined as cross, I would have defined as cross. Since I have written here as dot, I should write here as dot. So, if the flux lines due to I 1 and due to I 2, this is the flux lines due to I 2, if they are in the same direction, then I put the dot there, and if this is dot, then I will call this as cross, then I will call this as cross. What it is implying is that if I apply a voltage plus voltage, instantaneous positive voltage here, instantaneous positive voltage here, at that same instant this voltage is also positive. At that same instant the voltage V B1 dash is positive. That is what it implies, that instantaneously if the voltage is positive, this voltage is positive, the instantaneous this voltage will be positive, because the way the winding has been oriented, the current, a fictitious current in the sense is this need not flow, there need not be any flow of current, this could be an open circuit situation. But I think that if had there been a current in the direction in, as we have chosen a current direction in, if I choose a current direction in and that produces the flux in the same direction, then the voltage, instantaneous voltage of this terminal will be positive with respect to this one. So, therefore, I will call this as dot and I will call this as cross. Now, looking at this, let me now confuse myself. Let me now say that I choose arbitrarily current direction as this. Let us say A2 terminal, I have chosen the current direction as this, right, and chosen that this terminal is dot. I am chosen this terminal as dot. So, what is the, if the current direction is like this, current is going like this, current is going like this. So, what is the flux created by this terminal? Flux lines created by this terminal has a arrow of this, arrow of this, isn't it? The flux lines are going like this. So, this current is going there and this. So, these flux lines are now going like this, yes. So, it is going like this. So, therefore, let me decide whether this terminal, now this terminal I am just choosing, or you can choose this terminal, whether this terminal is dot or cross. So, since I have put arrow here in this direction, I will also try to put the arrow here, arrow there, and if the arrow there is there, then the current direction is plus is there. So, if the current direction is like this, then what is the flux direction? Flux direction of this line is, what is the flux direction of that? So, this is up, this is also up. Right, this is up, yeah. So, this is up. So, this up being this thing, if this is dot, now this terminal will be dot and this terminal will be cross and this terminal is cross. So, that means the instantaneous voltage, now you see if I refer it to the previous one, if the instantaneous voltage was plus minus here, this point potential will be minus plus here, because if this is cross terminal is plus, this cross terminal will be plus, this plus, therefore, minus, this minus will go to this minus. So, this is how we decide the dot and cross terminal polarity by looking at the winding orientation, how the winding has been done, and it is always done with respect to one reference. Any one of them you take it as reference and then with respect to that you decide the secondary terminal polarities in this case, right. So, with that I will come to the a few basic formulation of the transformer equivalent circuit. So, formulation of transformer equivalent circuit. So, in the while formulating the equivalent circuit, we must first assume a few important things. First assumption is that there are two ways of looking at it. One way of looking at it is first think that the transformer is ideal. First think that transformer is ideal. How do I define that the transformer is ideal? How do I define it? The ideal transformer has to be defined from the construction point of view. From the construction point of view, what we are defining is that one point is that this transformer, the magnetic material, number 1, magnetic material has infinite permeability. Magnetic material has infinite permeability. That is the one of the things we can think of. And another thing we can think of is the there is no loss in the transformer. No loss means, now let us look at this, what could be the loss in a transformer? Let us think about it. So, you can see that the loss is, one loss you are always very much familiar with is so called copper loss, and the copper loss is happening why? Because there is a current in a coil, there is a current in this coil, and there is a current in the second coil, and if there is a current in the primary coil, loss is there in the primary coil. If there is a current in the secondary coil, the loss is in there, and these losses are called copper loss, because the windings are made of normally copper, but nowadays sometimes aluminum is also used as a material. This material has to have high conductivity. The material, the coil has to be made of material that has high conductivity. So, therefore, it is normally copper is chosen, and even if copper is a very good conductive material, it still has some resistance, and therefore, there is some loss in the coil. So, it is a copper loss type is there, plus there is some other extra loss which we have not encountered so far, that is called iron loss. Iron loss or basically loss in the magnetic material, We will later talk a little more about it, but at this moment it is enough to know that this loss also can be divided into two components: hysteresis loss and eddy current loss. Still I want to little bit give a feel of it. What is hysteresis loss is, you understand that here all the quantities are AC quantities and sinusoidal AC quantities in most cases, though it is not necessary that this from the basic transformer principle that the currents and voltages have to have exactly sinusoidal shape, but most often in power transformers we encounter sinusoidal supply with which the coils are excited, and therefore, they produce sinusoidal currents, and the system being linear, consisting of only linear elements. So, the currents will be sinusoidal, and you know that the current will be sinusoidal and a little bit of phase shift will be there, some phase shift will be there. That is the only way a linear system behaves when sinusoidal excitations are applied. So, but with sinusoidal excitation, an interesting thing happens in the magnetic material. Magnetic material has some property or hysteretic property, in which the flux path does not remain identical, it does not follow the identical path while increasing compared to compared to the path when it is decreasing. So, flux increases and decreases through different paths. We call it a hysteresis path. It looks like this: flux increases and flux decreases. This is one path when flux is increasing. This is one path when flux is, this is flux. This flux is increasing, and this is MMF, that is magnetic, but that is a current essentially. So, when the current is increasing, flux is going through this path, and then it is reducing through this path. So, you see that it doesn't follow the same path. So, what happens is, it can be derived that every cycle there is some energy loss within the core. That loss is happening here, that loss is happening within the core, within the core, that loss is happening because of the cyclic nature of the flux increase and decrease. So, every cycle such amount of loss is there, which is proportional to this area of the hysteresis loop, and therefore, there is some loss called hysteresis loss within the thing. We will discuss it more detail maybe in future classes. And there is another loss which is also happening within the core. This is also happening within the core, and that is happening due to the exactly same reason of Faraday's law, that when there is a change in flux within the core, it is also inducing a voltage within the core. That means, the core itself is behaving like a coil, and that within that coil, since the flux is alternating, first is changing here and there, that is producing a voltage within the coil. A coil kind of thing is created within the magnetic material, not in the coil, not in the copper coil, but within the core, within the magnetic material, within the iron, there is a loop created and there is a current flow. So, that also produces a kind of loss, because it will have some resistance, and that loss is called eddy current loss. This current is called eddy current, and the loss due to that current is called eddy current loss. So, when the transformer is considered to be ideal, we assume that the magnetic material has infinite permeability, and we assume that there is no loss in the transformer, copper loss and iron loss. And the third point third thing that we assume is that what is that? That is called no leakage condition, no leakage flux, no leakage flux. What does it mean, a leakage flux? Let us see. What is the meaning of a leakage flux? Leakage flux is and there is a coil here. Let us say, what is a leakage flux? Suppose there is a current in this coil I1, suppose there is a current in this coil and this has a number of turns N1. Our basic electromagnetic law will say that this current, let us consider only this current here, and let us not consider immediately the current in the second coil. This is the second coil, second coil, and this is the first coil. This we named as A1 dash, and this we named as B1 dash. And when there is a current in this coil, as we have seen, these flux lines are created within the core. The majority of the, it is true, that is true. This is the majority of the flux lines are confined within the core. Majority of the flux lines are confined within the core, but some lines, as you can see, that which is linking the primary and but not going through that, but it is preferring a path through the air, this air. So, it is this flux line is essentially choosing an alternate another a minority of them, minority of the flux lines will choose an alternate path through the some part will be through the iron part and the remaining part will be the through the air gap path. Most of them, most of the majority of the flux lines will go like this, there is no doubt about that, majority of this thing. So, these flux lines which is linking the primary, these flux lines links primary, but does not link the secondary, is called leakage flux of primary. These flux lines, these flux lines indicate the leakage flux of the primary, and this flux line is a part of magnetizing flux, part of magnetizing flux. That means, these flux lines are part of magnetizing flux consists of flux lines created both by the current I 1 and I 2. Let us say there is also a current I 2, there is a current I 2, let us say the direction is like this, then that has also created some let me do it with red pen, that has also created some flux lines, right. These flux lines are created and they are linking, these flux lines are created by current I 2 corresponding in our words is MMF, corresponding MMF is N 2 I 2. These flux lines are created by current I 2 and they link both coil 1 and coil 2. So, they are part of the magnetizing flux. So, they are part of the mutual flux, that means this flux mutual flux, right, or magnetizing flux. And however, there is also another part of this thing which is created by the secondary coil, which is only linking the secondary. This flux line is links only secondary coil. So, links only secondary coil. So, this is called the leakage flux. This flux line will be defined as the leakage flux of the secondary coil. So, this is called the leakage, these flux lines indicate the leakage flux of the primary. This flux line is a part of the mutual flux. This is created by I 1 and links both coil 1 and 2. So, this is the practical situation. Actually, things will happen like that. If there is a coil and you pass current here, if there is a coil and you pass current here, or current gets passed, you pass or gets passed due to the load connection, due to the load being connected here, this side it will be initiated by connecting a voltage. This A1 dash terminal you will probably connect a voltage source and this side you will connect a load. So, these flux lines are initiated by that, and the moment there is a current flow in the secondary coil, that also contributes to the flux lines, overall flux lines of the core, because MMFs are there, all MMFs sum together and produce the corresponding flux line, and the relationship you already know, the total MMF divided by the reluctance is the flux lines, total flux lines. But this is mutual flux, because they are linking both the coils, and contribution of some part is coming from the primary coil current and some part is coming from the secondary coil. For example, this flux line is coming from due to the current I 1 and this flux line is coming due to the current I 2, but they are linking both the coils, whereas some flux lines are linking only one coil and not linking the other, and that flux line is called the leakage flux. So, for the simplicity, an ideal transformer should not have any leakage flux. So, if I consider that, I just come to the simplest model, that is what we should look into. So, what can I write then? Then overall what is happening is let us again start quickly drawing a transformer. And connect a voltage and then another coil, right, and connect a load. This is called load terminal, this is called source terminal, this is source, voltage source. This voltage source, let us call it as V 1 and this load is, let us call it Z L, and let the current, physical current is I 2 here and the physical current here is I 1 and the number of turns is N 1 and the number of turns is N 2 and the mu r is tending towards infinity. So, this is the ideal transformer which has no resistance, the coil has no resistance and there is no leakage flux, and this is the essence of transformer. This is how an ideal transformer behaves. The real transformer will be deviating, but not deviating too much. In fact, we have to find out how much it deviates. In fact, that is what regulation does. Regulation tries to find out how much it deviates from the reference, the ideal one. The ideal one is this. So, the ideal one has only two essential equations, One equation comes from the Faraday's law. First equation is Faraday's law, and Faraday's law says that if this is V 1, look at it, this is the supply and the source, and this being there is no resistance between the source terminal. Let us also define as if this is a source terminal and there is no resistance between these two terminals and there is no resistance between in the coil at all because of our assumption, then we can say that V 1 is equal to E 1, and then we can write that U 1 as per Faraday's law is equal to N 1 d phi m by dt. This phi m is the phi m created by combined effect of all the currents and MMFs. This is the phi m created by the combined effect of all the currents and MMFs. It is not solely due to the current I 1. This phi m is created by both current I 1 and I 2. So, this is the equation, first equation. So, how do I know what will be this phi m? So, how do I know what is this phi m? So, there phi m, in order to find phi m, I have to know that there is a magnetic circuit law. Using magnetic circuit law, we will determine phi m. So, how do we do phi m? This is what flux linkage law, concept of flux linkage comes. So, what is the flux linkage of this coil? Flux linkage of coil 1, because this equation can also be thought of as d dt of lambda 1. Lambda 1 is called the flux linkage of coil 1. So, what is the flux linkage of coil 1? What is the flux linkage of coil 1? Coil 1 flux linkage will be N 1 phi m in this case, n 1 phi m in this case, the is equal to what is that? It is created by whom? Created by the current I 1 and I 2. So, there we write what is the flux due to current I 1 and the coil inductance is L 1. So, if the coil inductance is L 1, which is equal to L m, L 1 into I 1, that is the current. I am writing an instantaneous equation. Please mind that this is an instantaneous equation, plus, or what is happening? Let us see, this current going here is this direction current is creating flux in this direction, this is this direction, and this current going there is creating flux in this direction, it is getting in this direction. So, the total flux linked by this coil is L 1 I 1 minus, if I do it a little elaborately, I can do it this way, L 2 I 2 is the flux linked by created by the coil I 2. However, flux per turn is divided by N 2 multiplied by N 1. This is flux linkage, this is flux per turn, this is flux linkage divided by number of turn. So, it is flux linkage per turn. So, therefore, that is the flux per turn into N 1, because I am talking about the flux linked by the coil 1. So, N 1 into flux, overall flux that is created is defined as L 1 into I 1 into this. Now, in this case no leakage, so we can think that it is equal to L m 1, otherwise no leakage, because of no leakage. Otherwise, we have to think that it is equal to L m 1 plus L 1, otherwise with leakage, right. Okay. And so, and no leakage, L 2 is equal to L m 2, no leakage. With leakage L 2 is equal to L m 2 plus L L 2 with leakage. So, this also has a new definition then, L 1 I 1, this thing we can combine it as mutual inductance between the coil 1 and 2 into I 2. So, you see that we can find out the flux from this expression. If I know L 1, if I know external current I 1, then I can find out what is the flux of the core, that is the overall flux that is developed due to the combination of the currents I 1 and I 2, right. So, this is the basic equation of N 1 phi m. So, therefore, in a circuit, why we are choosing this thing instead of flux, we are choosing what is the objective? Objective is instead of flux, write in terms of I 1 and I 2, L 1, M 2, these variables. Instead of a flux variable, you choose these variables, because they are measurable quantities. These are measurable quantities. So, Faraday's equation we are modifying in terms of the measurable quantities. So, therefore, we write it as U 1 is equal to d dt of L 1 into I 1 minus m into I 2, right. Right. Here we can do a little bit of modification in this equation also. We can write it as this is equal to L 1 I 1. Let us see some trick we are doing. So, what we will do is m into n 1 by n 2, let us do a trick, that means I am multiplying n into m 1 by n 2 into I multiply by n 2 by n 1. Let me do this thing, you see that n 1 cancels, n 2 cancels, n 2 cancels. So, I am just doing a simple trick by which I am multiplying this mutual inductance term into n 1 by n 2 and the current term. Therefore, overall keeping this equation unchanged. In order to keep the equation unchanged, I am multiplying I 2 into n 2 by n 1. So, if I do that, what I get is d dt of L 1 I 1. Now, m into n 1 by n 2, m into n 1 by m 2, we already know that it would be equal to L 1, okay, into I 2 dash. So, I am defining a new variable I 2 is equal to I 2 dash is equal to I 2 into n 2 by n 1, right. So, this is we define this variable. So, therefore, this is equal to d dt of L 1 into I 1 minus I 2 dash, which we can think that it is equal to L 1 d dt of I 1 minus I 2 dash. So, this is the equation of the induced voltage U 1 as a function of just I 1 is a function of the measurable quantity L 1 and two currents I 1 and a reflected current, we call it reflected current of I 2 in the form of I 2 dash, right. So, why this is becoming interesting is that we are able to replace every equation, just that means we can think that it is a equivalently I can think that the circuit is like this, I can think the circuit is like this. There is a inductor L 1 and there is a voltage, there is a current, there is a voltage U 1 which happens to be equal to V 1 in this case, and there is a current I 1 and there is a current I 2 is here, the arrow is here, I 2 dash, and that is what is equal to V 1. So, this transformer equivalent circuit in the case of this thing is essentially this one. So, what is the other unknown here? Other unknown is E 2, and E 2 will be going by what law? It will be simply going by the same law. It is n 1 n 2 phi m d phi m by dt, which is nothing but n 2 by n 1 into d dt of n 1 phi m, which already we have found out. So, this is nothing but U 1, this is nothing but n 2 by n 1 is nothing but this quantity we have already found out is as U 1. So, we get E 2 by U 1 is equal to n 2 by n 1, right. So, this voltage is V 1, this current is I 2 is this one, right. So, we have got the relationship between two voltages, nothing but number of turns relationship, and we have got the relationship between this. Then the last magnetic circuit relationship would be that what is the value of I 1 minus I m. What is the value of I 1 minus? Now, think this way, what is phi m in general in a magnetic circuit? Phi m would be what? MMF by reluctance. This is the basic equation NF circuit, and what is the MMF here? N 1 I 1 minus N 2 I 2 by reluctance. Reluctance R is the reluctance of the magnetic path. Now, R, as you know, R is equal to L core length by mu of the core and cross sectional area of the core. This is all dimensions of the core. So, you also know that if mu c tends to infinity, reluctance tends to 0. Therefore, what is happening is reluctance tends to 0, but phi m is finite, phi m is finite, not 0, not 0. So, what we are getting is N 1 I 1 minus N 2 I 2 is equal to reluctance into phi m. Since reluctance approaches 0, this also N1 I1 minus N2 I2 is approaching tending towards 0, because this reluctance is moving towards 0. Phi m is finite. Why phi m is finite? Because we have seen phi m is completely decided by the voltage equation. We have seen that phi 1 is nothing but the voltage equation. Since E 1 is there has to be phi 1. N 1 is a finite quantity. If there is a voltage applied, there has to be finite phi m, finite, because E 1 is a finite quantity. So, phi m cannot be 0. How can be 0 then? Obviously is reluctance. If reluctance tends to 0, then MMF balance situation tends to 0. So, which means that we are getting a very important criteria, that N1 I1 minus N2 I2 is equal to 0 for an ideal transformer, for an ideal transformer, right. So, what all things we have to remember? In an ideal transformer, U 1 by E 2 is N 1 and E 2 by, or U 2 by U 1 is N 2 by U 1, and this is N 1 I 1 is equal to N 2 I 2. This happens. So, if these two things happens, what happens? Then you see that we get corresponding to that V 1 or E 1 I 1 is equal to E 2 I 2. This follows this follows this, E 1 into I 1 is equal to E 2 into I 2. This is called, that is what we started with. We proved that for an ideal transformer, this is the instantaneous power balance. This is what is known as instant Okay. So, thank you all those who have attended this class. In the next class, I would like to continue the discussion and show you the differences of between an ideal transformer and an actual transformer. What way they affect the equivalent circuit, that will be discussed in the next. But today we have discussed some very important thing. We have understood the flux, the MMF balance situation, and how the mutual flux is created in a transformer.